So I'm happy to introduce our last speaker from the first part of today's session, Andrew Schopieray from Pacific Institute for the Mathematical Science and University of Alberta, who will tell us about doubly rational finite groups. Thank you, Andrew.
Thank you, Julia, and the rest of the organizers for inviting me. And thanks to PIMS and University of Alberta for paying my salary currently, and Canada for letting me stay here for the time being. What I want to talk about today is a topic that sits at an intersection of actually 3 other projects that I'm working on, and it seems to be the most fun aspect of them to talk about. And so that's why I've chosen this topic. It's very straightforward to explain, and hopefully most people can get something out of the talk. So our topic starts with finite groups. So if you have a finite group, then one thing that you typically do to move into a categorical setting is to look at its category of representations. And here I'm doing everything over the complex numbers, nothing incredibly fancy. But if you want to make it sound fancy, you can note that this is a symmetrically braided spherical fusion category, if you want to make it sound as complicated as humanly possible. So this just means that the tensor product, when you look at the double braiding on pairs of objects, that's completely trivial. It's the identity for everything. And we like to pretend that we're very advanced human beings mathematically, but really what we want to understand is linear algebra. That's the tool that we use to study everything. And so what we do once we pass to the category of representations is we try to get some numbers out of it. And for the category of representations of a finite group, we typically look at the character table. So the character table, as hopefully we're all familiar with, is looking at traces of endomorphisms, or you can think of just as traces of the representations. So we get very simple arrays of numbers. And here I've illustrated just for show the character table for the cyclic group of order 2. Now, you can go down this route, but you can also go a different route when you're looking at categories corresponding to finite groups, which is to look at what we would call representations of the quantum double, or in a purely categorical sense, the Drinfeld center of G-graded vector spaces is another way to think about it, which gives something which is not symmetrically braided, but it gives something which is the polar opposite, something which is non-degenerately braided. So there is no simple representation, which the double braiding is trivial with all of the other simple representations. So these are sort of foils of one another. They are 2 things that are good to study side by side because of how distinct they are. Now, associated to the non-degenerately braided fusion categories, we get what we typically call the S matrix. And rather than taking traces of endomorphisms, our spherical structure on this category allows us to take traces of these double braidings. And we get this invertible now array of numbers, which wants to be the character table of the finite group. So it wants so bad to be a character table, but it just isn't quite a character table, but we'll come back to that a little bit later. So keep this array in mind, because the next slide is going to have the exact same form. So again, starting with our finite group, now rather than describing these numerical invariants, let's change everything into questions. So a very classical question about finite groups is, are the entries of the character table rational? Or since they're algebraic integers, are the entries of the character table integers? And this question is quite old, but it's also quite difficult. And one name for these. You might see various names for these groups, but they would call these rational groups. And so that's the word that I'm going to use to describe them. Finite groups whose character tables consist of integers. And again, this is a very difficult problem. You can go quite a ways back and find sort of partial results, which haven't been extended or updated, I guess, in the past 50 years or so. So for example, a result from 76 states that if G is a rational group and it's solvable, then the only primes dividing the order of the group are 2, 3, and 5. So you've restricted yourself at least to a small number of primes dividing the order if the group that you start with is solvable. So this restriction does not exist for non-solvable groups. For example, all symmetric groups are examples of rational groups, and clearly we can make those as big as we want and have as many prime divisors as we want. So why not just ask the same question on the left side of the screen? Ask, are the entries of the S matrix of the quantum double rational? Or, since they're algebraic integers in this case, are they integers? So obviously, if we're asking this question about the double of the finite group, a sensible name for this would be a doubly rational group, a group whose S matrix of its Drinfeld double consists of just integers. So that's also a sensible name, because if you're doubly rational, then you are certainly a rational group. And that sounds very mundane, but these doubly rational groups, it's hard to emphasize how strong of a condition this is. It's an oppressively strong condition compared to being a rational group. So this really should be a very small slice out of these rational groups, but we find that it's actually quite a large number of them. So an optimistic thing to say would be that this is a potentially easier problem, but you very quickly realize that in fact, that's way too optimistic. But as an example of how this might be slightly easier is that with our current knowledge of non-degenerately braided fusion categories, if G is a doubly rational finite group, then only 2 and 3 can divide its order. So in terms of order, you're cutting down the number of primes. Unfortunately, you've kept the worst one, you've kept 2, which pretty much consumes all finite groups. That's the joke theorem that all finite groups are 2 groups. So we've kept a lot of these groups, even though we've eliminated the prime 5. So an example of this is S4. So we're not allowed to include primes 5 and greater. So the symmetric group that's largest that we can include is S4. And sure enough, it's a rational group, but it's also a doubly rational group as well. And you can explicitly compute the S matrix of the double, and you get the following. So you can see it from the outset that the size of this double is growing quite large. It's really a square more than a double. It's almost squaring the size of the information that we need. And so this data ends up getting quite large very fast. So there are very few examples that fit within the confines of these slides. So for an infinite family of examples, I'll denote the cyclic group of order n by Cn. Since we're only allowed the primes 2 and 3, an obvious way of constructing these groups might be to take cyclic groups of order 2 and cyclic groups of order 3 and have them act on each other in various ways and see if the result is one of these groups. So sure enough, if you take the cyclic group of order 2 and you act on any number of copies of the cyclic group of order 3 by inversion, sort of the most obvious action, then this whole infinite family are doubly rational groups. So if you let K be 1, you may see that C2 semi-direct product C3 in this way is a familiar group. It's just S3, written in a way that you might not have seen before. And when K equals 2, if we calculate the rank of the double, we see that when K equals 2, the rank is 381. The rank is 44 already. So even the second entry in this infinite series is massive. But using a scale box, I crammed the S matrix for that onto the slide. Okay. So you can see that studying this from just the perspective of the S matrix in sort of a combinatorial way might be inefficient just because of how much data is growing in such a fast rate. So why stop just at these doubles? We have a whole theory of non-degenerately braided spherical fusion categories for which these questions are also applicable. And another name for these categories is modular tensor categories, which you'll probably hear more about this afternoon and into Monday as well. So, and again, this is a more specific definition of modular tensor categories. But the question translated into this setting is, which modular tensor categories in general have integer S matrices? So a solution to this question would include the doubles of all of the doubly rational finite groups, but it also contains much more. And so this question just explodes in difficulty from the finite group case. So one reason is that if I take this, what we might call a piece of the modular data of the modular tensor category, its S matrix, then I can have many modular tensor categories which have that same S matrix. This data, this numerical invariant of these categories, isn't as descriptive as we might have hoped. It certainly does not characterize modular tensor categories. So as an example of this, here's a very modest S matrix. Really, it only has 1s, 2s, and 3s. Looks like some, oh, it's got a couple 4s in it as well. So this is a very mundane example. But this S matrix has at least 8. While I was writing this, I could come up with 8 off the top of my head. 8 modular tensor categories which have this exact S matrix. And so even at a very small rank, the amount of modular tensor categories for every S matrix is already starting to grow. And it's only going to get worse as the rank increases for very silly reasons. So this question is actually much more interesting than the finite group case for this reason. So moreover, just as a very quick proof, one of the rows or columns of this S matrix consists of positive numbers, in this case, positive integers. And these correspond to Frobenius-Perron dimensions of the objects. And if we add up the squares of all these, in this case, we get 72. So if you didn't notice, that's not a square. And these doubles of finite groups, their dimensions are always the square of the group itself. And so none of these 8 categories that correspond to this S matrix are doubles of finite groups. So even if we did look at S matrices whose Frobenius-Perron dimensions were squares, we would still have this many-to-one correspondence, but we can even fill in the gaps in between. So it really is a much larger world of modular tensor categories with integer S matrices. So why would we study these things? The first one is something that mathematical researchers very often don't think about or actively avoid, which is that these examples provide very pedagogically basic examples. Okay, so what do I mean by this? I mean by this that when you look at very simple modular tensor categories, or in particular at their S matrices, often you end up with a matrix whose entries are big sums of roots of unity or something, and it's even difficult to write them on a slide when they're rank 6 or 7 without using some sort of a formula that you have to compute. So if you're trying to introduce someone to modular tensor categories or just give very basic examples of why formulas work, you don't want to be giving these incredibly numerically intensive examples just from the get-go. So I think these are a very relaxing introduction to the world of modular data because everything is just whole numbers. It's quite nice. And of course, as I mentioned before, this explicitly describes a very large class of solvable, because only 2 and 3 can divide the orders of these groups. Very large class of solvable rational groups, which this has been an open problem for over 50 years. And so if we can't describe this incredibly small slice of these, then certainly this question about all solvable rational groups is out of reach. So the third reason that you might want to study these, you might hear more about on Monday, I think, from reading the abstracts, is to understand something about this Galois action on modular tensor categories. And these integer S matrices sort of represent the kernel, very loosely construed, kernel of this Galois action. So the Galois action, just to remind you, if you aren't familiar, is that if I have a modular tensor category with a tensor unit 1, then the characters of its Grothendieck ring, or of its fusion rules, are exactly given by, they're in one-to-one correspondence with simple objects in this category in the following way. You get a character by sending an object to the Berlinde eigenvalue given by this quotient. So that's why this S matrix is not quite a character table, because there's this slight scaling involved. And the Galois action, if I have some Galois automorphism, again, these characters take values in the algebraic integers. In fact, cyclotomic integers of a very predictable order. Any Galois automorphism of that field in which these character values lie corresponds a permutation of the simple objects, which is just applying the Galois automorphism to the character itself. Okay? So you can think about this as a permutation of characters, but because of the correspondence with simple objects, it's really a permutation of the simple objects. And so clearly, if all of our entries of our S matrix are integers, then modular tensor categories with integer S matrices are precisely those modular tensor categories for which this Galois action is trivial. So every Galois automorphism does nothing to your category. So you can think about that as giving you no information about the category, but by giving us no information, that's actually giving us quite a lot of information about the category. Okay. So the conundrum about this is that it's very possible, which you'll hear about on Monday, to completely classify modular tensor categories for which this Galois action is transitive. So the Galois automorphisms transitively permute all of the simple objects. You can write down a list, a very small list, one family of modular tensor categories with that property. So you would think if you go to the diametrically opposite end of the spectrum, and you look at categories for which the Galois automorphisms do nothing, everything is a fixed point for every Galois automorphism, that you would have an equally easy time writing down examples. But it turns out that that's a completely different level of difficulty. Okay? So it's quite interesting how different those two cases are. So there's lots of interesting things about these particular categories. So I'll end with just a small set of examples. In fact, none of the examples that I gave, well, I think the very first example that I gave with Z mod 2, that is an example of nilpotency, but the other examples are not. So if you assume that you start with a modular tensor category with an integer S matrix or trivial Galois action, which is also nilpotent. So by nilpotent, I mean we look at the following sequence. I take the universal grading of my modular tensor category and look at its trivial component. And then I just keep doing that over and over again. And nilpotency is what you would expect, that this eventually terminates in the trivial category with one simple object. So this might seem like a very strong restriction, but for instance, this is automatically true if we look at these categories which have dimension which is just a power of 2, just like for finite groups. So you are still getting an incredible amount of examples which are nilpotent. So one benefit of this is that several fellows back in the mid-2000s showed that nilpotent modular tensor categories are almost centers of finite groups. Okay? So that's summarizing this very briefly. So in particular, we have to make a slight tweak to that, which is that we have to look at twisted centers of finite groups. So this is some additional cohomological data that we associate to this double. So some people call this the twisted double of the finite group. And the almost part is that we may have to tensor our category with something which only consists of invertible objects. But we don't have to look too far. So in fact, in the case of these categories with trivial Galois action, you can cut down the dimension of this pointed category to just 12 different dimensions. So it's very small. So when I say that it is close to a twisted center of a finite group, I mean that in a very concrete way. So our examples, which are nilpotent, actually can be written in terms of some finite group data. But we can be even more specific than this, because we also have a characterization of fusion subcategories of twisted centers of finite groups for all G and all of these 3 cocycles omega, which came from the same time frame. And in particular, for each non-degenerately braided fusion category or modular subcategory, as we have in the case of the previous slides, corresponds to some subgroup data. So 2 mutually centralizing subgroups whose composite is the whole group, along with some non-degenerate symmetric bi-character on their intersection. Okay? So it still is a lot of data, but it's very explicit in this case. So in theory, heavy emphasis on in theory, nilpotent modular tensor categories whose Galois action is trivial can be characterized explicitly in terms of a uniform collection of subgroup and cohomological data of nilpotent groups. Now, what do I mean by uniform? So I mean that typically when I'm describing these modular tensor categories with trivial Galois action, I can describe them in terms of finite groups, but as I look at larger and larger examples, you find that you need more and more data to describe how to construct these categories. But here in this special case of nilpotent categories, we have a way to describe them, which the number of pieces of information that I need isn't growing as the size of the category grows. So there's a very small set of data that you need to describe these. So this also eliminates this issue which you arise to as you try to study this from the S matrices themselves. So if you study from the S matrices, then you have to worry about this issue of multiple categories corresponding to the same S matrix. But in this restatement, in the nilpotent case, you avoid this issue. They're all just contained in some of these centers. Now, the additional issue which arises in this situation is that we have twisted centers of some nilpotent finite group. And you can show that in almost every case that that actually has to be a rational nilpotent group, which you're looking at the center of. But nilpotent rational finite groups, you keep searching through the literature hoping that eventually you'll find something which has a complete classification. But no, nilpotent rational finite groups are really far from being understood as well. And so even if we are able to write some abstract nonsense characterization of these modular tensor categories with trivial Galois action in terms of nilpotent rational finite groups, then really we're just comparing two things that we don't understand, but we know that they're sort of the same in some way. So this categorical question hopefully will eventually shine some light on these classical problems, but it's far from being understood. And just one last thing that I would like to mention is that you could also look at these doubly rational finite groups just by order. And you can very quickly compute what all of them are up to order 100 or so. And you can start lumping them into families. And it's quite amazing that all of the finite, doubly rational finite groups of order less than 100 sort of all fit into nice families, except for a couple. And I don't think that these are exceptional in any sort of way. It's just that we haven't found what infinite family they belong to yet. So there is still some hope that you could use some sort of brute force method to lump all of these into families. Okay? And you can imagine how big the doubles of a finite group of order 100 are. They're absolutely massive. And we're already seeing that they fit into nice families. So I think it's a very interesting problem for a lot of reasons. And you'll see these examples appearing in other projects as well, because to me, they're sort of the most basic examples, as I've mentioned before, at least from a number theoretic perspective. So I think I'll stop there, just in the interest of time, and thank you for listening.